I welcome all of you to the class. As far as today's class is concerned, today is our lecture 7. Today is our lecture number 7. And in the previous 6 lectures, we talked about the stress. We gave the basic definition of stress. Now, today we'll be talking about one more physical quantity, one more idea, one more concept associated with the stress, and very important in dealing with the deformation of the bodies. Okay, and the concept is called strain. Today we'll talk about the strain. Let's suppose we have a machine element. And this machine element is, say, for example, a rod. Let's talk about a rod is a machine element. And this machine element is having length, say, for example, L. L is the length of this machine element. And its area of cross section is, say, for example, A. If, say, for example, this machine element is subjected to a normal load of P, okay, then under the influence of this normal load, what will happen? Essentially, the length of this machine element will change. And we say that this machine element has undergone, this machine element under the influence of this external load P has undergone extension. It has extended. This is what we call as extension. It has undergone extension. Originally, its length was L. Now, let's suppose the extension in the machine element is by an amount delta L. Fine. So we write initial length of the machine element is equal, initial length is equal to L. Change in length, change in length is equal delta L, and the final length, we write it as the final length. Final length is equal to initial length plus change in length, that is L plus delta L. Okay, we define physically a term as, we call, since as far as the deformation is concerned, as far as the change in length is concerned, the change in length has happened in the direction of the load. Okay, if you look at the change in length, the change in length is in the same direction as the direction of the load, and this change in length is in this direction, which is actually perpendicular to the area of cross section. Okay, so this change in length is in the same direction as the direction of the normal drawn to the area of cross section. We call this as, this change in length, we first, let me define, we call it as, we define the term as strain. And strain is defined as change in length, that is delta L, divided by the original length, that is L. Delta L divided by L is defined as the strain. Returning back to the concept I was trying to illustrate, since this change in length is in the same direction as the direction of normal drawn to the area, okay, we call this type of strain as the normal strain. This is called the normal strain. And this normal strain, if we treat this to be our x-axis, if we treat this to be our x-axis, we write this as, this is normal strain along x-axis. We write this as eta xx is equal delta L divided by L. Okay. In the same way, if we have, say for example, if we talk about if we change the direction of the load, let's change the direction of the load. Instead of applying the load which tries to elongate the machine element, this is in fact called tensile load. This is called the tensile load. Instead of applying the tensile load, if we apply the load which tries to change, which tries to decrease the length of the machine element, that is, if we try to apply the load in this direction, apply load P. Okay, this load P is called the compressive load. This is compressive load. Okay, this is the compressive load. Originally, if the length of the machine element was L, okay, now as we apply the compressive load P, the machine element will, its length will decrease. Okay, the final length will be only this much. This will be the only final length. Okay. Let me redraw my diagrams. We had the compressive load acting on the machine element, tries to deform it. We apply the load in this direction, load P, and this load P will try to decrease the length. Okay, so there is a change in length. I will call this as delta L. So initially we started with length L. Okay, so we said initial length. It's quite easy to comprehend. Initial length is equal L. Okay, change in length, change in length is equal to delta L. Therefore, final length, final length is equal, final length will be L minus delta L. This is the final length. Okay, and we define the strain, since again it has caused the deformation in the same direction as the direction of the normal drawn to the area of cross section. We write the strain again eta xx. We write this as change in length, that is delta L, divided by original length, that is L. But we put a minus sign here. The minus sign represents that there is decrease in length. There is decrease in length. This is how we do it. So this is what we call as strain. In fact, we should be very fully aware that this is called the normal strain. Not so there, as we had two types of stress, the normal stress and the shear stress. In the same way, we have normal strain and the shear strain, which we'll be discussing later on. But important is the understanding that we are talking about the normal strain. Okay. Now, there is a relationship between this load P, whether it's compressive or it's tensile. Okay, it sets up the stress in the machine element. That's what you call as the normal stress, which we have already learned. It creates the normal stress in the machine element, and normal stress we were representing by sigma xx, something like that. Okay, now this normal stress, let me call this a sigma x, is created inside the machine element. Okay, and it tries to resist, it tries to resist the effect of, it tries to resist the effect of external deforming load. It tries to resist the effect of external deforming load P. Okay, the external load P is trying to deform the machine element. Okay, in response to the external deforming load P, the machine element inside sets up the small loads, internal forces. Okay, those internal forces per unit area is what we call as the stress. Okay, now, so when there is a stress in the machine element, okay, this stress is created in response to the external deforming load, and this stress or the external deforming load is also responsible for creating change in the geometry of the machine element, or change in the dimensions of the machine element. Okay, that is, stress is responsible for creating strains in the machine element. Okay, so it means associated with stresses are the strains inside the machine element. If you look at this example or the previous one, so we had the normal stress, what we call as sigma. We had the normal strain, that was eta. Now, as we keep on increasing the value of the external deforming load P, the value of the normal stress will keep on increasing. And in response, the value of the normal strain will also keep on increasing. So we write this as sigma normal stress is directly proportional to the normal strain. In a machine element, as we apply the external deforming load, it creates the stresses inside the machine element, as well as the external deforming load is also responsible for straining the machine element. Okay, so straining the machine element, tending to cause deformation in the machine element, the machine element tries to resist the effect of the external deforming load, and it creates up or builds up the internal stress. It builds up this stress such that as you keep on increasing the value of the external deforming load, the value of the strain will keep on increasing, and in response, the value of the stress will also keep on increasing. So we write sigma is directly proportional to eta. If we remove this sign of proportionality, we write this as sigma is equal some constant E and this eta. As far as this constant is concerned, this is a very important constant as far as the solid mechanics is concerned. And this constant is essentially known as, we call this constant as the Young's modulus of elasticity. This is called Young's modulus of elasticity. Okay, we call this as Young's modulus of elasticity. Young's modulus. Now, how we define it? So we write sigma is equal to E times Young's modulus times the strain. Therefore, we can write the Young's modulus is equal to stress divided by the strain. Okay, for eta equal to 1, that is for unit strain in a machine element, for unit strain, the value of sigma becomes equal to the Young's modulus. That is, we define it as, let me claim this diagram. Therefore, we can now define the Young's modulus of elasticity as, we can define it as, therefore, from this equation, we can define Young's modulus of elasticity as, Young's modulus of elasticity, Young's modulus of elasticity is the stress generated or created or produced, generated in a machine element under load, when a unit strain is reduced. Okay, so whenever you have a machine element and this machine element is subjected to external deforming load P, when this external deforming load creates a unit amount of 1 unit amount of strain in the machine element, okay, at that time the stress that is generated in this machine element is equal to the Young's modulus of elasticity. And we can further write it as, we have sigma is equal to Young's modulus times the strain. We can write it sigma, the value of sigma is Newton per meter square or Newton per mm square, okay, is equal to Young's modulus times the strain, and strain is dimensionless, it does not have dimensions. Okay, so we can write this as the value of E, the value of Young's modulus, sorry, the unit of Young's modulus of elasticity is same as the unit of stress, that is Newton per mm or per meter square. That's it. As we go ahead, let me talk about again the cross. Let me take up an example. Let's say we have a machine element. Okay, let's suppose its length is 3 meter. It is subjected to a load of 10 kilonewton. Its area is 5 mm square. Okay, its Young's modulus of elasticity, E, is 350 into 10 raised to power 9 Newton per meter square. Okay, so we are asked, if you are applying a load of 10 kilonewton on a machine element having area of 5 mm square, okay, and original length of 3 meter, Young's modulus of elasticity of this material is 350 into 10 raised to power 9 Newton per meter square. Okay, how much is the stress? How much is the normal stress created in the machine element? And second, how much is the value of normal strain created in the machine? And this is quite basics. Okay, so we can write, as far as normal stress is concerned, that's equal to the external load, that is 10 kilonewton, that is 10 into 10 raised to power 3 Newton, divided by the area. Area is 5 mm square. Okay, 1 mm is 10 raised to power minus 3, so it will be 10 raised to power minus 6 meter square. Therefore, the stress created will be 10 raised to power, so it will be, let me rub it, the value of the stress will be, it will be 0.2 into 10 raised to power 10 Newton per meter square. That's equal to into 10 raised to power 9 Newton per meter square is the value of stress that will be created. How much is the strain? We know stress is equal to Young's modulus times the strain. Okay. Now, if you look at the stress is how much? 2 into 10 raised power 9 Newton per meter square is equal Young's modulus of elasticity, that is 350 into 10 raised power 9 Newton per meter square multiplied by the value of the strain which we have to find. So 10 raised power 9, 10 raised power 9 Newton per meter square will cancel. Therefore, the value of strain will be 2 divided by 350. This much will be the value of the strain created in this machine element. Okay, so this is how we have to go ahead. Sometimes there may be a problem like this, like stress is equal to Young's modulus times strain. For this circular cross-section bar, we can also write this as stress is equal to E times the strain. Stress is equal to P by A is equal to E times the change in length divided by the original length. Okay, so this formula is quite handy in solving few fundamental problems. So this is what basically we have in, we keep on discussing as far as the values of stress strains are concerned, as far as the fundamental equation between the normal stress and normal strain is concerned. And this equation, stress is equal to Young's modulus times the strain, this is what we call as the Hooke's law of elasticity. This is called Hooke's law. Okay, this is what we call as Hooke's law of elasticity. Quite simplest form of Hooke's law of elasticity. Okay, so this is how we define it. Okay, this is what we talk about the normal stress and the normal strain. And we have a little introduction about, we need to give a very simple introduction about the shear stress here as well. Shear strain will be taking a separate chapter, but yeah, we should be simply talking about the shear stress. Let's suppose we have two machine elements, and those two machine elements are in this form. Like this. Okay, these two machine elements are, say for example, are are riveted together. Okay, we have a rivet. So you have machine, yeah, let's call this as plate 1, let's call this as plate 2. Let's say plate 1 and plate 2 are connected together with the help of this rivet. Okay, let's put this rivet. Okay, so now let's apply load P in this direction and also apply a load P in this direction. Okay, so as we are applying loads in these two directions, so if you concentrate your attention on this area here, okay, because this rivet will have some area of cross section. Okay, if you concentrate your attention on this area of cross section, this area will tend to move in this direction, lower part, and the upper part will tend to move in the left side direction. So if we separate it out and draw the diagram for it, so it will be like we have a rivet. This is the lower portion of the rivet. Okay, this is the upper portion of the rivet, and this is the lower portion of the rivet. This is what will happen to it under the influence of these loads. So this portion, the lower portion, will tend to slide in this direction, and the upper portion will try to slide in this direction. So you are having load P acting, you are having load P acting. So if you look here, this surface out here will try to resist the deformation created by this load. Okay, now say for example, these two portions are in equilibrium, they are not moving at all. So if you separate this lower portion or the upper portion, we can draw the free body diagram for the lower portion. As on the lower portion we are having load P acting. Now at this surface we need to have an opposite load, let's call that as P dash, so as to balance the effect of this load P when the system will be in equilibrium. Okay, such that P dash will be equal to P, the magnitudes will be same. But this load P is acting in a direction, when this type of deformation has happened, this load P is acting in the direction of, is this load P is acting in the direction which is parallel to this area of cross section. Okay, or it is perpendicular, this is area vector, this is your area vector, the load is acting in a direction perpendicular to the area of vector, and we said that the stress which will be created by this load is called the shear stress. We call this as tau is equal P prime or P divided by A. This is what we call as the shear stress. Now let's repeat the same diagram. Let's say we are adding up one more plate. Let's add up one more plate to this system. Add up one more plate to this system. Like this, okay? And these two portions are now riveted together. Let's suppose we are having a rivet here. Okay, this is the rivet now. Apply load on this plate, P. Apply load on this plate, let's say P. Okay, now look, as you are applying load on this plate in this direction, this portion will try to move in this direction. This portion will try to move in this direction. Separate out this rivet. So we'll be having one portion of the rivet here. Okay, another portion of the rivet will be here. Okay, and another portion of the rivet will be somewhere here. This is how the deformation will happen. And if you look at this lower one, if you concentrate your attention on this, separate it out, separate it out. Okay, on the top portion you'll be having resisting load in this direction that will nullify the effect of this load, and on the lower area you'll be having the resisting load in this direction. Okay, that will try to nullify the effect of this load. Okay, let me, by equilibrium they will be P and P. Now look, compare this area, compare this area, this one. Okay, compare this area with this one. Here the machine element, portion of the machine element is subjected to shear stresses, but the shear stresses are on the opposite faces, on two faces, phase 1 and phase 2. This is also the shear stress. Okay, but we call this shear stress as double shear. This is called the double shear, because this machine element happens to be under the shear stress, but the shear stress happens to be on its two surfaces. Okay, this is what we call as the double shear. So we are having the double shear, and we're having this is called the single shear. So shear stresses on the machine element can be the single shear as well as the we can have the double shear. Now let's take a few problems from the book to solve the questions based on stress is equal to Young's modulus times the strain. The problems where we have to calculate the single shear and the double shear, and then we'll be discussing the mechanical properties, and then forward we'll be going to some other topics. This is where I end up today's class. If you have any questions, you can ask. Thank you very much.